Okay, thank you, Will, for reminding the link to the slides, and also we can ask questions at any time, and they were checked basically on our Slack channel, and also on the chat on Zoom. So, welcome everybody, and thanks to be here to the session dedicated to the crowded stellar fields, which is chaired by Michael Rich and me. And also thanks to all the people that collaborated to this session, Annalisa Calamida, Will Clarkson, and Kelly Hambleton. And I will go with some friendly reminders. We all signed for the code of conduct. We strongly believe in this code, and we are encouraged to follow. And also the talks will be recorded and videos will be posted. And of course, if you appreciate the talks and the session, you are encouraged to show your appreciation and put some questions and a thumbs up. So this is the agenda today. We will have a session on welcome and introduction, and then we will move with Colin speaking about the updates on the forced photometry pipeline, and then we will move with Jan, who will tell something about the difference image analysis in crowded fields. Then we talk about, there is a bit change here, about some notes on variability search in the Galactic Bulge. And then we will end with the talk by Christian Johnson and Michael Rich, who will present the slides on massive PSF reduction in the bulge. And as you can see, we will have only a few short talks because most of the session will be devoted to sharing thoughts and discussion on the possible problems and issues with a so tough topic. So, Mike, do you want to?
Yes, I have an opening remark here, and I'm just gonna, if I can share my screen, I think, so I'm just gonna briefly show this as the motivating factor, which is, what can we do? Can everybody see my screen? I'm wondering if actually, yeah. Okay, so the motivating factor behind this session was that originally the project did not have very good treatment of extremely crowded field photometry. In fact, 2 years ago, I actually visited Colin with our graduate student at UCLA, and we started to compare the Blanco-Decam Bulge survey with what was achievable from the pipeline of LSST. And the answer was, it wasn't very good. But LSST has dramatically improved. Of course, the project, the Rubin project, has improved the treatment of crowd fields. And this is what you can gain. This is our Blanco-Decam Bulge survey analysis, and this is decaps and pan stars. And you can see the improvement in the color magnitude diagram, depth, narrowness of the red giant branch, recovery of bright stars. These are things that you can definitely gain by having this advantage of treating crowded fields better. I'm just trying to, unfortunately, I'm having some technical difficulty. There we go. And trying to advance the slide here. This should do it. This should give a better, okay. And then I'll stop with this, but here's an example of what you can gain. This is using UGR photometry on NGC 6656. And with good crowded field reductions, you can actually see the multiple populations here. You can get a color magnitude diagram that is close to HST quality. So it really pays off. And that's all I have to say. I'll stop my sharing.
So I think we're still seeing the same slide, but oh, there we go. Thank you.
Yeah, there, okay. Yeah, so that it really pays off. And I think it's worth putting the effort in because it will enable a huge range of science, not just crowded field science, but all sorts of other science that relates to interesting things like strong lensing, galaxy clusters, and so forth. Certainly the community that is interested in everything from dwarf galaxies to globular clusters to rich clusters in the plane and so on will benefit. Okay, and so that's why we want to improve the attention to crowded fields.
Okay, thanks a lot, Michael. And I think that we can move to Colin. Will speak us about data management perspective on crowded fields.
Okay, thanks, Massimo. I can go to the next slide. So I sort of want to start off with a bit of background about what data management's requirements are in terms of crowded fields. What's our perspective on this topic? So I think it's important to first highlight that data management's requirement that we're accountable to the NSF for is to support image differencing in all areas of the sky. This mostly stems from the observatory's really unique capabilities in terms of time domain science and our view that image differencing gives good access to that time domain science and variables and transient stars, both at low latitude and high latitude. And a consequence of this is that it means that we must succeed at all of the image processing steps that get you to the point of being able to do image differencing. So that means we must do ISR, astrometric calibration, photometric calibration, those types of algorithms over all parts of the sky. And we must do that well enough to support image differencing. And like Yusra said yesterday in the science pipeline session, we sort of view these kind of core algorithmic components as something that the project is best equipped to handle because we're closest to the camera and the telescope and we have access to the sort of full set of data. So we sort of prioritize making sure that those processes are robust and successful in order to support all the downstream science that comes from there. And so Ian's talk afterwards will tell you more about our performance in that area. Next slide, please. So crowded field photometry itself remains a best effort goal rather than that level of requirement that we're accountable to the NSF for. That's not to say we don't see the merit in this. We certainly see, in particular in Mike's slide a second ago, the value in being able to do simultaneous stellar fitting like a typical crowded field code. And so as a result of that, there's a technical note number 129 that I've linked there that reflects our thinking for how we would integrate simultaneous stellar fitting in the DM pipelines. This is something I described in more detail in the algorithms workshop, and you can find the video there to go into all the details. But the core message is that the detect, fit, subtract, redetect cycle, that's really critical to crowded field code. We would do that on coads and then use the sources and positions from those measurements on coads in order to fit fluxes on individual visits to obtain that time series information. This is sometimes called force photometry, but it's a little bit different because we're simultaneously fitting multiple sources in that force photometry mode. And just to kind of to test that our pipelines And the infrastructure that we have is capable of supporting this type of simultaneous fitting mode. We have a working prototype that uses our PSF models, WCS solutions, background fits, etc., inside the DM stack. And so next slide, please. And so this is just a slide for aficionados to kind of show that we're not talking about vaporware here. This is just demonstrating that prototype at 3 different densities of images. The top row is the original, the bottom is all the sources and their measured fluxes subtracted from the image. So ideally that residual will be a nice noisy image. You see there's still lots of work to be done here. There's still lots of room for improvement, but this just kind of demonstrates that we do have simultaneous stellar fitting in a functional state, if not a full pipeline. And so next slide, please. And so I just want to end here by saying that we know that the international contribution process is wrapping up the decision-making process and starting to finalize the agreements and define what the contributions are to that process. We know that lots of contributions are in the realm of adding software to do other various post-processing steps to our images to produce value-added catalogs, and in particular crowded fields. And so I just wanted to take this opportunity to say that we look forward to working with these contributor groups to make sure that our processing enables them to get as much science out of their downstream processing as is possible to really enable as much science as we can. So that's all I have. Thanks.
Okay. Thank you. Thank you so much. And sorry for switching off my camera, but I have a problem with my driver, and this is a long-standing problem. Who knows me already knows the problem. Well, we will move to the talk by Jan Sullivan. We will talk
Massimo, shall we ask questions?
Sorry.
Otherwise we are behind. So there's a question for Mike. The question is from Michael Woodwathy, and is, can you define excellent treatment? What is the change in parameter or algorithm you are suggesting in recasting for crowded field photometry? Mike,
this is a question.
Okay.
Yeah, this is a question for me. If you could please repeat the question. I didn't quite follow.
So can you define excellent treatment? What is the change in parameters or algorithm you're suggesting to perform crowded field photometry?
Well, I think an excellent treatment would be kind of something that you would know by the result you achieve. You know, in the BVBS survey, we have used DAO and multiple passes, which has resulted in this quality of photometry where we can reach the main sequence turnoff of globular clusters 8 kiloparsec distance and produce close to HST-like quality. And so what I say is the 2 parameters of excellent treatment would be capability to not crash in even the most crowded fields, like 500,000 stars per square degree, that is the middle of the bulge or the center of the Magellanic Clouds. Certainly, you know, to not crash. The second requirement would be to produce the best possible result that one could achieve.
Okay, there's another question, more of a comment from Nut. HST has a resolution of 0.1 arcsecond. At very best, Rubin images might have 0.4, 0.5 arcseconds. If crowding is limiting factor, that's 3.5 magnitudes in depth. Hold on a second.
Yeah, no, I expect Rubin to outperform HST, but what is surprising, and this is not just a quality of, you know, we've achieved with DE-CAM, but also Subaru, the gain in aperture does help because of the signal to noise ratio. And surprisingly, in many programs also, I don't want to take up so much time here. but you get an outcome that is better than you would think. In other words, the large telescope with the excellent ground-based seeing can punch above its weight. And there's another point. There can be lucky imaging cases. There can be cases where seeing is as good as 0.4 arc seconds, in which case, in practice, the competition between the 6.5 meter equivalent aperture of the Rubin versus HST is not as great as one might think. So the argument really is it's worth trying to recover the best possible crowded field photometry because you can do surprisingly well.
I guess Knut wants to comment on this because I see a raised hand.
Yes, yeah. So Mike, I just want to point out that there is, you can calculate what the depth limit for a given resolution is. And it's nice to have a big aperture because you will reach the crowding limit faster, but it's really the image resolution that's the factor. So I mean, I think a quantitative metric would be, if the pipeline is able to get within some percentage of the theoretical crowding limit, that is something you can measure. But seeing how far you get down the main sequence of a cluster will depend on what that cluster is, where it is, all these things. So it's not a very quantitative way to.
No, I'm not. I wasn't proposing it as a metric. I was mainly showing those figures as an inspiration to encourage the development of software that would do two things. One, potentially in the long run, sort out cases of lucky imaging. And second, that would do close to what one would say the very best reasonable extraction of the photometry. And we don't know whether that would be co-adding frames or reducing across different frames, all frame. So I don't want to say that LSST can compete with HST, although I think there is the potential, as I'll show in Christian's talk, there is a potential to do things that HST can't contemplate doing.
Okay, thank you. So we also have a question on Zoom. So I believe it's to Colin, it's from Charles Liu, and it says, could you please explain again the difference between typical forced photometry and your forced photometry?
So when we talk about the image differencing pipeline, we say that we'll detect a source and then we'll do forced photometry for all the different visits that source might have fallen, or that object might have fallen on in the past. And so that just fits that single PSF to all those different visits. In the crowded field context, we would take all the sources in an image and then fit them simultaneously. So your flux in one particular source is also affected by our ability to fit out the flux from its neighbors. And so the positions are still fixed, which means it's forced in that sense, but it is a slightly different operation than we typically talk about in other contexts.
Very cool. I'll ask you about that more as time goes forward. Thank you. That's very interesting.
There's another question for Colin, if we have time on Slack.
I have a question if there are.
Yeah, but can we ask? It's a question from Tom Wilson. You wrote it like before, so.
No. Please go ahead with Tom.
Yeah, so he says, I haven't read the MTN 129 in detail, so let me know if the answer is just to actually read the document. For crowded field iterative photometry, thus detect, subtract, fit, redetect, refit for the end force iteration detection, that is, detect star A, subtract, find star B. Do we then fit both star A and B, or keep the original position flux of star A and then just fit for star B position and flux? This is the question from Tom Wilson for Colin.
Sure. So the way to think of this is that we detect all the stars. So we detect A, B, and C. We fit them all simultaneously. Think of it as a big sparse matrix. subtract off all their best fit fluxes. And then that meant in many cases reveals a new source that you weren't able to see because it was in the wings of a previous star. So we add that source and then we go refit all the stars we know about, A, B, C, D, E, F, and so on.
Okay, thank you.
Cool. I have a question. Colin, is there any plan to put together the forced photometry with the simultaneous fit of all the neighbor sources within a given radius and at the blender? And maybe this could help in very, very crowded regions such as the corals have some globular clusters.
I think the way to think of this probably is that we sort of see the simultaneous fitting algorithm as kind of a well-known solution to a well-known problem that kind of has its own, provides a solution that we can characterize and understand well. And so we'd kind of like to pair that, not like combine that with a deblender, but just be able to look at the product of the simultaneous fitting and then look at separately the output of the deblender. Combining the two is a bit more like beyond state of the art, that we're trying to just limit ourselves to state of the art only here for the moment first.
Okay, thank you.
But you do make use of the fact that stars are stars in the deblender potentially. So there is some sort of slightly larger overlap than you, without doing extra work, you get some overlap. But of course, the deblenders are designed to handle complicated extragalactic fields with no knowledge that things are stars, so which is why we need both the branches. But I think the overlap may be not quite as bad as we're imagining. We'll see.
Okay. Thank you very much.
Massimo, I think we can defer some of the other comments question to the discussion, since it's like a question about what it's really crowded field photometry and difference between point sources and extended sources. So instead of like stopping here, we can defer all these comments to a later discussion. Is that fine?
Yeah, I think, yeah.
Okay.
So we can move to the crowded field processing with the science pipelines. Thank you, Jan.
Okay, thank you, Massimo, and everyone. So I'm going to do a small case of what Colin was describing. This is one particular test that I did late last year and early this year of making the Rubin science pipelines be able to successfully process the data from the DCAM Galactic Bulge survey done by Saha et al. So the data that was used for this was the Galactic Bulge survey from 2013 and 2015, down selected to only using fields B1 and B2 and bands G and I. Wanted to have multiple fields, multiple bands in order to make sure I wasn't isolating on one special case band, but this was not meant to be a complete processing of the entire survey. So it was restricted to just these bands and these fields. Those two fields do overlap slightly, and I believe are some of the lowest galactic latitude fields in the survey. So they cover some very high stellar densities. There's a number, if you go to the link here, DMTN 171, it is also linked as a bookmark in the Crowded Fields channel. You can find a lot more detail about the setup. A large part of this investigation was to do a stress test of our current pipelines. I'll note that when I was first running this, I think it was 95% of the observations crashed. They simply would not run. However, by the end, there were very, very, very few that we were unable to process. So we found and fixed many of the bugs, and all of this is in the science pipelines as of release 21. We're at release 22 now, so we have advanced a bit beyond this even. Next slide, please. Just to give an overview, this is a very crude coad of the total fields. So all of the observations built into templates and mosaicked. Just to give an overview of the shapes of the fields, you can see there between the BA1 and B2, there's slight overlap on the image on the left. That is the coad itself. On the right, that is the N image, or the number of observations that contributed to each of the pixels that are selected for this coad. You can see slight overlap there. I didn't end up actually getting anything of great value out of the overlap regions, but it was helpful for finding if there were any bugs when we went from around 40 observations to more around 80. Sometimes you can have other bugs creep in at that point. Next slide, please. So in that last slide, there was a little red box in the upper left part of field B1. This is CCD 23, just the coad selected to match CCD 23 to be used as the template for one of the observations. You can see these are in fact quite crowded fields. We went a little bit further and also were investigating how difference imaging was going to perform in these fields. Next slide, please. This is the difference image for that CCD and that observation. I didn't show the science image because it looks very similar to the template. The important detail from this is that while we can see various image subtraction artifacts throughout the CCD, if you go to the next slide, please. When we zoom in, the image subtraction artifacts are mostly dipoles and some ringing structures, all of which we are familiar from our regular reprocessing of more sparsely crowded fields. And these artifacts are not significantly overlapping. So while we might have more imaging artifacts and some real sources in the difference image, it is not a fundamentally harder problem, it looks like, than for the sparser fields. Next slide, please. And for some reason, only one of the, oh, there's the other figure. Okay, it just took a little while to load. So these shown here are a histogram of the density of sources that we detected at 5 sigma within each of the observations for this field B1. On the left, G band, and on the right, I band. Overlapping in the histograms are the 2015 and 2013 data. Overall, the 2013 data had much worse seeing than 2015, and that is reflected particularly in the I-band observations, where the 2013 histogram is peaked down at around 200,000 sources per square degree, while in 2015, we're achieving up to 500,000 sources per square degree fairly consistently. Next slide, please. We haven't done too many consistency checks of these sources, but one that I did do was giving the source counts to check that we are not seeing a drop off in the number of sources as we go to fainter magnitudes. We do see a couple observations where something in the photometry pipeline has failed. I believe this is due to PSF modeling errors. Fortunately, this is an avenue that people in science pipelines are actively pursuing. And as we move to newer and more sophisticated PSF modeling tools like PIF instead of PSFX, it is possible that that will fix some of these errors. each of the colored lines in this plot is a different individual observation. So you can see with the variable seeing is causing the magnitude drop off at a different point in all of them. However, as you go to better seeing and a fainter magnitude cutoff, we are covering the same source count curve, which indicates to me that those sources are real. Next slide, please. So in conclusion here, the current state of science pipelines are in fact able to process and measure sources at densities greater than 500,000 per square degree under good conditions. And it looks as though some of the issues that were identified a few years previously may have been fixed within the pipelines, and it does not appear as though we are significantly undercounting sources at these fainter magnitudes. Within the difference imaging, those residuals appear reasonably isolated, which gives me good confidence in doing science or improving on those difference images, because we're going to be improving difference imaging for the rest of the survey already. I've highlighted here just a few things that have occurred to me that are going to improve our crowded field processing because we are improving them for the rest of the science pipelines. That's, as I mentioned before, the better PSF models, the improved image differencing. And one thing that I didn't mention before, but is gone into in the tech note, is speed and performance enhancements. To this point, we have mostly focused on improving the scientific accuracy and robustness of the science pipelines. And we are beginning to work on performance tuning of more of those algorithms that we have written. So some of this processing did take much longer than the typical processing time that you may have heard for a CCD for Rubin. The longest was about 4 hours for one CCD on one chip. But that is something that we are actively working on, and a more typical case would take 2 minutes at the just with the pipelines as they are now, and that's with significant performance enhancements that we know we can make. And a final note, we are going to keep reprocessing this data in the future, both to check for improvements or regressions, and in the future that will all be using the new Gen 3 middleware. This particular processing run that I've presented here was done using the old Gen 2. And that's all. Thank you.
Thank you, Jan.
So there are some questions. First question from Chuck Claver. Have you been able to compare the color magnitude diagrams from Sa et al. With those derived from the Rubin science pipelines in the two selected fields, B1 and B2?
Good question. I'm afraid I haven't been able to do that. I was at the point where I was working on this processing. I also took over as the TCAM for alert production, and my amount of time for doing data processing and analysis has decreased since then. So I wasn't able to do more sophisticated analysis like that.
Okay. Another question in a single image from Firoza Sutaria. In a single image, how will you distinguish an artifact from a transient if the subtraction is poor at the core of the galaxies?
So this is an image differencing question. So I have a few different answers for that. If the subtraction is very poor, say it is at the wings of a saturated star, I'm afraid we are likely to lose that. If the subtraction is poor because our algorithms haven't advanced enough in one particular area, then say at the moment, if the science image has better scene than the template, but that one is one that we imminently will have working better, then a future release of the science pipelines may be able to process this cleaner. Beyond that, what we're going to begin working on within alert production, we've actually begun on it, but we'll be developing it in sophistication soon, is machine learning for real bogus. And identifying a true transient in a poor subtraction is a good candidate for real bogus classification.
Thank you.
Okay, we also have a comment on Zoom from Michael Rich, who says it was an excellent presentation, and it would be also great to see the resulting color magnitude diagrams. And he even goes on to say it would be nice to present the results in a website that would be updated as new results arrive, e.g. comparison and color magnitude diagrams become available.
Absolutely. I'd say that is an area that I would greatly welcome collaboration from the community, as within the alert production team. We want to make sure that our pipelines can run and produce reasonable results. And so a big part of the focus of this investigation was making sure that our pipelines would run, because they didn't before. And I don't have a lot of time right now for making these additional added on features like that, but I would love to help someone put that together with me, and that is something that we would could I agree that would be a very useful data product to see, and especially when we do future reprocessing, it would be nice to have something like that where we would be able to see the evolution of those results. I guess the short answer is, if you are interested in that and have a bit of time to help put it together, please contact me and I will try to make that work.
Thanks so much. Maybe you could just provide your email address or something in Slack, or a way to contact you.
Sure, of course.
For your Slack information. Thanks.
There's another question by Nut. Did you look at model subtracted images in addition to the empirical different images? How do they compare?
That's a good question. I'm afraid we did not look at the model subtracted images. So these difference images are using the standard Allard and Lupton subtraction. So we are fitting, we are fitting that matching kernel and convolving the template with it before doing the subtraction. And so we have not gone and done, say, Colin's sophisticated model subtraction that he was describing in his previous talk.
Okay.
There's another question.
Okay.
Do you have time to ask that? So
I can answer it. Yes.
If you want, maybe you can answer directly on Slack, and so we can keep going with the presentations. Yeah.
Okay. So this is part of the work that we did within the TDS Crowded Photometry Task Force, and just by chance we reduced exactly the same data set discussed by Jan. So the idea behind was to start dealing with the very crowded fields and massive data sets to understand from the point of view of the user what are the problems behind and the best techniques to find variable stars and characterize them. And we selected this single individual chip around the globular cluster NGC 6569, for which we already know some of the variable stars in the field from Ogle. And we reduce all the data with our frame, which is a PSF algorithm, which performs simultaneously the position of the fluxes on all the available images. So we have a set of images in different, with different filters, and we fit a master list to each of the images. And just a quick comment on dataset. We have to say that the dataset is not the optimal proxy of the Rubin dataset, because as pointed out before, there were a few data collected in 2013 and 2015, so there is a huge time gap and within the observation, and the observation were collected during a few nights. So definitely some type of variable stars are missing from this data set. In any case, in the field we found 117 Ogle variables, but also we provided additional 30 strong candidates with good light curves, which apparently were overlooked by Ogle. And we are still analyzing the light curves, but this mismatch with Ogle probably is not due to the different photometric limits, because we found also two or three strong RRA variable stars missed by Ogle, and that in principle they should be absolutely the reach of Ogle. But probably the most interesting thing is that I read the document mentioned by Jan, and I asked him to send us his catalogs to cross-compare our catalog with his catalog. And so we made this cross-match, and we found that the DIA analysis found 93 out of the 117 Ogle variables and 22 out of the 30 new candidates on the global analysis. But when we compare individual images, we found only a minimum number of 2 to a maximum of 25, 30 variables in the individual image. Here in the image, you see the Ogle variables depicted with the cyan circles. Yellow circles are the new candidates, and red crosses are the DIA variables cross-matched with our frame. How can we read those numbers? The frame catalog is based on the whole data set, and basically on 53 R-band images, and the full DIA analysis was performed on a subsample of them. We found 41 images, so there is a small mismatch. It's a 20% less. And so basically the two approaches roughly give the same numbers, but we need a complete analysis, however, that we are performing within our task force. Instead, single images give much less robust answers. And probably this is an important point for the alert brokers who will have the duty to analyze the outcome of the DIA analysis and take the history of individual detection, memory of the light curves, and so on. And I think that was more or less all that I had to say. Thank you.
So there's a question by Marcia. Are you worried that all-frame processing may be too slow to process efficiently the actual Rubin LSST images?
Yes, this is an excellent and a thorny question, in the sense that we are aware that processing all the for example, the bulge or all the galactic plane with the frame definitely takes a lot of computing time, unless we use very, very specific facilities. For example, a supercomputer which is able to do a parallel work on the analysis. But probably, well, there is the idea of some kind of contribution on that to offer to community an frame reduction of some specific areas of interest, which can be discussed, of course, with the community, because this is a delectable in-kind contribution. So we are open to discuss this.
Okay, thank you. Colin has a raised hand.
Yeah,
sure, cool. So can I double check my understanding of your global versus individual detections? So it sounds like most variables created a detection at least at some point in the sequence of images, but for any single image, most variables did not show up on that single arbitrary image. Is that the right understanding?
Yeah, you are right, Colin, but our analysis is absolutely preliminary. What we did is to cross-match all the DIA catalogs of the individual images and do a general catalog, and we cross-match with our catalog. And then we did the same for individual catalogs. And the next step will be to understand what happens when you move from the general, the global catalog, let me say this way, to individual catalog, to see, for example, if the variation is too small or is overlooked for some reason that we still do not know. So this is just a very preliminary analysis.
Thanks. That's really interesting.
Thank you.
We can move on, I guess.
Okay, I can stop my share. And Michael, are you ready with your presentation?
Yes. Do you have it uploaded, or should I? I'm having a little difficulties with the screen sharing, and then I'm getting multiple windows appearing and so on that I can't quite resolve. If you're able to share the presentation, that would be great.
Yes, I just have to.
If not, I'll give it a try.
Do you have a link to your presentation? Because I don't have it.
No, I did upload it, but it seemed like the upload was overwritten somehow. So I'm going to try to see if I can just do this here and share screen. Oh, now I'm. Is everybody seeing this?
We're seeing
no, it's just black. Oh, yes.
Oh, yeah.
Okay, good. Okay, so we'll just go with this. This will work. So I'm doing this. I have the wrong presentation. I really apologize. I just opened up the wrong presentation. Let me just get the correct.
Michael, we can see your whole desktop. So if you just there we go.
Yeah. Okay. Yeah. I'll. There's a problem occurring here. Okay. How's this? Is this okay?
You have to push up the. Yeah. Now it's okay.
Yeah, okay, great, thank you. My apologies. So I'm presenting on behalf of Christian Johnson. We're co-principal investigator of the Blanco DCAM Bulge survey. I'll also try and move these. Okay, I'm trying to move the pieces out of the screen here. Okay, good. I'm not sure you can see the bulge in the optical is, of course, that you primarily get much more about age and metallicity from the optical colors. The importance of U, which is relevant to the project, is the vast, if we focus our attention on the vast number of metal lines that occur, going back to the work of Nancy Roman, Egenlin, and Bell and Sandage, that the U band information about metallicity that can be accessed in the symmetry. So this shows the Blanco Decam Bulge survey. This is a 200 square degree area. So this is now, we're dealing with hundreds of fields, hundreds of observation. For example, 10 billion detections of 250 million unique objects. So there is the potential for this to be an LSST or a Rubin Observatory Pathfinder project. The yellow field in this frame has been reduced and largely de-reddened, just to give an idea. So you can see the large area compared, for example, to the SAI-L 2019, where similar conditions of being and so on. And this shows, you know, we've already seen what crowded fields are like. And I must say that I express my admiration to the project for being so successful in now fields in excess of 500,000 stars per square degree. This particular data set face the problems of merging data sets that are photometric and terribly non-photometric conditions, and also long and short exposures, so that we would get the benefit, which is very important in the bulge, because the bulge contains members that are extremely bright, and in many band passes as bright as 10th magnitude. Of course, you want to try to go as faint as you can. And you like also Christian developed this whole data is pretty complicated because you have
Michael, you're cutting out. We didn't hear you a little bit there.
Oh.
And also, there's about a 10-second delay between you changing the slides, or several seconds between us seeing them. So maybe if you could just wait between switching slides for a few seconds, that'd help. Thanks.
Thank you. Can you hear me? This slide, we can.
And maybe if you shut your video off, that might help too.
See, do that just a moment. So. I'm just having trouble locating where to shut the, unfortunately, I'm using multiple screens here due to another technical, video. Hopefully that will, or is there still a problem with the,
the sound seems to be better. The sound seems to be better, thank you.
Okay, sorry, my apologies. Okay, so you could see this is the pipeline that Christian developed, and there's the main thing is that you process each of these with PSF fitting, but then you have to determine 0 points on a nightly basis and apply extinction and air mass corrections and all of these 0 point correction. I'm sure the project is taught extensively. That's why there's a monitor telescope. Here's an important slide which shows the benefits of different fewest sources. DuPhote, a very wide, better than source extractor. Good. So with Christian, I'm sure that the program. Oh, sorry.
I think, yeah, we cannot really hear you well. It's cutting in and out.
Oh boy. Okay. Is this better? I'm going to speak very close to
Yes, yes, this is better.
Okay, okay. So you can see that DAO photo project is doing is far superior. And I'm just going to skip this slide. This shows how the data was processed at Indiana. Of course, the project will do something different. And this shows, the number of overlap regions that had to be combined. So a lot of data management. This will be something, of course, that the LSST project will have under control. I will skip this as well, but this shows how the coordinate matching was undertaken. And I would urge you to contact Christian if you had any additional questions on that. This shows how the photometric solution was transferred between different frames. Arrow point to a transfer, a red or arrow, a red or blue arrow is a 0-point change. And it was very important to, so to speak, flatten everything to a common photometric 0 point. This will be important in all crowded field work, of course. And then in the next slide, you can see in this particular field, there is substantial reddening that he accounted for. And you could see this very large reddening vector here, which is corrected using an analysis by Simeon et al. And so one of the things as we get close to the plane is that it will be useful to some kind of pipeline de-reddening. You can see the benefit of this. Here's a globular cluster color magnitude diagram, and here you can see a color magnitude diagram of the field. So you get excellent results. Now, the comments about HST quality photometry, and then I'll just show this slide here briefly, which you can read. And down the road, we would also like to take into account proper motions. So as the one important thing for the project to bear in mind is that there will be a long baseline over which these fields will be acquired, and proper motion corrections will be important over that time frame, and also the development of a pipeline reddening correction. Just briefly, some results. One can correlate U minus I with high resolution abundance measurements, and this has produced abundance distribution measurements for the red stars over the entire field of the bulge. You can also separate out the red and blue clumps and metal pore. You can clearly see the famous double or X-shaped bulge here. And finally, you can see that study multiple populations in globular clusters, you actually get a better result because you're able to sample out to 10 effective radii. You improve on HST results. So the improvement for cluster science over HST is being able to, and that's the end of the presentation, is being able to sample over such a wide effective radius of the cluster. In other words, studying the objects in question with a wider field allows you to work with less crowding. And you have the bigger aperture, you have somewhat less crowding. So the advantage, so you can do better science. Then you can compete with HST in that way. And that was what I meant to say, noting Newt's comments that yes, of course, theoretically, you cannot go as deep as HST. There is a huge difference, 3.5 magnitude difference because of the crowding limit. And that's the end of this.
Thank you.
Sorry, very sorry for the technical difficulties.
Oh, Will has a question or something to say. You're muted.
Thank you. I just have an announcement since we're almost out of time. As a scribe, I will be pasting the Slack discussion into the live notes sometime after this meeting. So if you have any Slack comments you do not wish to see in the live notes, please let me know in the thread that you see in Slack there. Thank you.
Yeah, and I think people can keep discussing and answering questions, asking questions on Slack, even if the session is over, correct?
Yes.
I also have a quick comment. Unfortunately, we ran out of time, but there are a lot of important things to discuss. Probably we can continue to discuss on the Slack channel. For example, the role of the number of sources, because we saw very interesting numbers. For example, 500,000 stars shown by Jan and per square degrees, I mean, and up to 10 million stars in the DECAM fields. And this could be interesting when we compare these numbers with the numbers provided by the galactic models, for example, by Trilegal. And also, I would like to discuss the role, for example, of the U-band, which would be really important in disentangling different stellar population in the galactic field because of the dependency on the metallicity. So I think that there is no room to discuss other
perhaps
topics.
we could run a little bit over time for those that are interested. Aren't we just running into a break, and maybe a discussion in the moment might be useful?
I think so. Even if I don't know if the session is stopped automatically at any time. I don't know if the organizer can tell me something on that.
The session will keep running unless I end it, but I'll point out there's also a coffee room Zoom where you can take things during the coffee time.
I would propose that since we're here, that we maybe give 5 minutes to the people that are here today to comment and ask questions and so on. Would that be okay?
I will stay here until you're done. Yep.
Thanks.
But maybe you want to take a moment to end the session so people can give a round of applause and leave if they have to.
Okay, well, the formal session is over, and we're going to have 5 minutes for general comments and questions. And so if anyone would like to applaud all the speakers, please do so. And thank you very much for attending, by the way.
Thank you a lot.
Thank you so much. Massimo, would you like to mention about our task force?
Yeah, of course. Everybody who is interested in discussing these topics and contributing is more than welcome to join our crowd field task force. There is one in TVS, which is chaired by me and Kelly, and also there is another one in the Stellar Milky Way local volume collaboration, chaired by Michael. So I think that it will be useful to continue the discussion within these task forces. Thank you.
So I will put the information for at least the TVS task force in the Slack comments now. If you're a part of TVS, then you're just welcome to join our Zoom meetings. And if you're not part of TVS, then you should sign up. Right, thanks.
Yes, and I'll put my email and contact me if you're interested in joining the crowd field task force.
Maybe, Michael, maybe you could put that into the Slack channel so it'll be preserved.
Oh yeah, as soon as I can find the Slack channel for this meeting, I'll put it in. Yes, thank you. I'll put the information in.
And to get an idea of the commitment, how frequently do you guys meet?
We haven't really, from our perspective, well, maybe the we haven't really formally met yet over in Stars, Milky Way, and Local Volume. And I'm very impressed by the progress of the project. Thank you, Ian. That was an amazing result. Very, very encouraging. What about the other task force?
We meet every 2 weeks. So if you're interested, please join. And I think there was discussion actually at one point of joining the 2 task forces. So maybe we can.
I think it would be a very good thing for these 2 task forces to join, and maybe, you know, since it's most critical for DBS, I think just joining these 2 together, I'll be in touch.
Okay, thanks.
Yeah, I agree, absolutely.
Any other comments, questions on this session? Okay, well, I really appreciate all the presentations, and also delighted to see the great interest in the community, and I really extend my compliments to the project for its dramatic progress in the processing of extremely crowded fields. Okay, so I guess we can end this session, and thank you very much, Massimo, for your excellent organization.
Oh, thank you too. Thanks, Will, Kelly, and Anna. Thank you, everybody, for joining us.
Thank you, everybody. Okay, and we'll continue in Slack.
Bye-bye.
Yeah. Okay, I think that I can stop the recording and close the...
You don't have to. As soon as it seems like people are gone, I end the meeting for everyone, so it'll stop.
I do have a question, Max. Maybe we can discuss this in. It doesn't need to be recorded, but maybe we can discuss this in Slack. We should work out what the chairs are going to say for the wrap-up session that happens in about 23 minutes.
Yeah.
Should we have that discussion in Slack?
Yeah,
okay.
Absolutely.
Cool.
We will meet on Slack in a few minutes. Okay.
Cool. Thank you.
Right,
May I close?
I just want to check, is next Wednesday going to be the next crowded field meeting? Because I know we've had a bit of a break because of this meeting.
I will be on vacation next week, so I think that we can start. Yeah, thank you. Thank you.
Okay.
Melissa, may I close the window?
When you're done, I'll end the session for everyone as the host when I leave.
Thank you.
Okay.
Yeah, thanks, guys.
Thank you. Thank you.
Bye. Thank you.
See you in the breakout summaries.